Okay, hello everybody to this week's ISGC seminar talk. This week's speaker is Yi-Ming Hu. He received his PhD in 2015 from the University of Glasgow and is currently a professor at the Yat-sen University in China. Thank you very much for agreeing to give this talk. The stage is yours.
Thank you very much. Can everyone hear me clearly? And during this stage of presentation, as long as you have any question, just interrupt me, okay? I'm very happy and honored to be here to present you this topic on the gravitational wave astronomy with TianQin. As Tobin introduced, I'm Yi-Ming Hu from Sanya University, and these pictures you can see here are basically the building sets, actually one of which I'm currently in here. This is a building I'm working in. So some whereabouts to gauge you better on where we are, and this is the city of Zhuhai. I'm currently in this city Zhuhai, and to have a better comparison, it's very close to Hong Kong and Macau. And we have a zoom in plot here showing this shaded region is the Sanya University Zhuhai campus. The main campus is in Guangzhou, but here in this region is the TianQin Center. And on the top of the mountain is our laser ranging facility. And you can see the ocean here. So our university has a direct contact to the beach and the ocean, which is very nice. So I welcome everyone, if you got the chance, to definitely consider coming and visiting us. Okay. So if we zoom in this TianQin Center here, we have a drone picture, and this is a TianQin building here. There is a ground simulation facility, and there is a cave laboratory goes into deep, like there are 100 meters in length. It's not very deep in the underground, but it goes into the mountain. And on top of the mountain, we have the laser ranging facility, which you can see this very nice view on top. Okay, so that's some background introduction. I want you to have some idea of where we are and the geographical locations of us. And to start the talk, I want to give you some instructions on what is TianQin and what can TianQin do. Then we can briefly introduce how we are going to perform some data analysis about TianQin. So the basic idea of TianQin is that this is a space-borne gravitational wave detector. There are 3 detectors, and each pair of them are linked with lasers performing laser interferometry. And by using this laser interferometry, we can measure very accurate the displacement between the 2 satellites, and we can use this information to reconstruct the passing gravitational wave signals. And you might be more familiar with the more famous European and American-led counterpart, the space-borne gravitational wave mission called the LISA. And the major difference between LISA and TianQin is that TianQin is geocentric, meaning that the satellite is orbiting around the Earth, while the LISA mission and simultaneously also Taiji mission, also from China, is proposed to be heliocentric, which is that these satellites are orbiting around the sun. Okay, and because it's geocentric, that means we have a limited choice of the arm length. We have to make it smaller. The arm length relative to LISA is like an order of magnitude smaller. And but the principle is the same. We use laser interferometry and the draft-free control to make sure the measurement of gravitational wave. And this is an illustration, the animation of TianQin orbiting around the Earth, and then together with the Earth orbiting around the sun. Now, of course, this is not to scale. And the actual orbital period for TianQin is about 3.65 days. To be exact, it's 3.64 days. So you can do the math very quickly that for a year time, the TianQin will be orbiting around the Earth for like 100 times. Okay, and if you are not familiar with Chinese, the Mandarin characters, then you might ask about the name. Why the name TianQin? So TianQin basically compose two parts, the Tian and the Qin. Tian means heaven above us, and the Qin is like the hub in the space. So we are aiming to launch a hub in the space so that we can use this instrument to measure the gravitational wave in the space. And there are many people in our institute working dedicated to the experimental part. Now, for me, I am totally, ignorant of these details on how to make sure the sensitivity curve is achieved. For us astronomers, the only important thing is this curve. And as long as we got this equation and then we put them into the computer, and this is a sensitivity curve we can deal with. So how to decipher this sensitivity curve is that the horizontal axis is the frequency. You can see it goes logarithmically from 0.1 millihertz to 1 millihertz to 0.01 hertz, etc. And the vertical axis shows the basically what we usually call the jargon is the what we call the ASD, or the square root of PSD, the power spectrum density. Now, this thing is basically a measure on how large the expected noise will be in different frequencies. And you can see that it goes up in the lower frequency. That means the noise level will increase in the lower frequency. And the lower it goes, right? The lower value it goes, it means the smaller fluctuation due to the random noise, and the better, because we want to measure weak signals, and lower noise fluctuation means that even if it's a very weak signal, we are able to detect it. And the absolute value here is something like 10 to the minus 20. So a typical strength or the amplitude of the gravitational wave signal is something you can compare against with. So this is the idea of TianQin. Now, with this sensitivity curve, we can just draw on top of that with some different typical gravitational wave sources. And by doing so, we can go through them one by one to ask the question, how many different sources can we observe, and how many of them we can observe? And through the several studies we have performed, we concluded that the typical sources TianQin can observe are these 5 sources. Now, there are many names calling the galactic compact binaries. That's GCB here, and also includes the VB, the verification binary. The only difference between VB and GCB is that GCB is something we believe they exist by theoretical derivation, and VB, the verification binaries, are something we have already observed through electromagnetical observation, through optical or X-rays. And we have the stellar mass black hole binaries in spirals, and we have massive binary black hole mergers, these corresponding to the BBH and MBHB. And also we have the extreme mass ratio in spirals, that's M-ray here, and we have also the stochastic background. The background itself is not very easily seen on this plot, but we can see the foreground, which is with a similar idea, and it goes the purple line here. Okay, so sometimes I think it's confusing to remember all these jargons, but the most important thing you can try to memorize is that gravitational wave sources are usually dominated by binaries. And if you look at the binaries, you can classify them as masses. So you can think about the binaries as 2 large mass components. That's one case, which is massive black hole binary mergers. And if you have 2 smaller mass objects that corresponding to the stellar mass counterparts, they can be the stellar mass binary black holes, or they can be galactic compact binaries. When we are talking about galactic compact binaries, usually they are dominated by white dwarf binaries. And the third category is you have 1 very heavy and 1 very light. So these corresponding to an extreme mass ratio, and that's an M-ray. Okay, so basically you can just classify them into by their mass components. And the 5th one is a stochastic background. That is something you cannot individually resolve, but they are just humming together into a total background, and then this thing becoming something that it looks something like a noise, because the statistical property of them are basically indistinguishable from noise in a sense. But their origin is from astronomy, from cosmology. So that is something we can use to distinguish them from the instrumental noise. And for the past years, we've been developing this white paper called the Gravitational Wave Astronomy with TianQin. And now this, we also call them the TianQin Astronomy White Paper. It has been recently published in last year in the Journal of Reports on Progress of Physics. And in this work, we've been trying to gather the opinions and basically by asking them questions, by asking the colleague astronomers questions. If we have this instrument called TianQin, how do you expect this machine to reshape our understanding on astronomy and on different aspects of astronomy? And we have been gathered these ideas, and the answer is that we, with this advance of TianQin instrument, we will be able to usher our understanding on three aspects, which is stellar physics and the growth and birth and growth of massive black hole, as well as the intermediate regime, the highly dynamical region around the massive black hole. Now let's go to the details. First of all is stellar physics. So far, we have been established some idea, some knowledge on how the stars evolve, and we can also predict something about the binaries evolution. But there are something in the binary evolution which is very intriguing, very interesting, but until this day, something that is not very easy to answer is the exact detailed physics on the common envelope process. This is something that astronomers expect to happen when you have two stars being very close to each other, and during the red giant phase, some component can grow very, very big, so it can basically contain both stars inside, so they share the same envelope. And during this stage, it can be very, very quick. In an astronomical term, it can happen only like thousands or 10,000 years. But the physics goes inside is rich. There are many mass and angular momentum and energy exchange. So the exact evolution after this common envelope phase can be very highly complicated and divergent. And so far, the observation on the outcome of the common envelope process is very limited. So we know nothing, or well, we know very limited on exactly what happens during this common envelope process. The good thing on TianQin is that we expect to see a large number of white dwarf binaries. And this is DWD means double white dwarf. Sorry for the jargons. And the idea is that we expect to see like tens of thousands of these white dwarf binaries. The same applies to LISA also. So with this large sample of sources, we can look at their statistics and then answer the question like what quantities are conserved in this common envelope phase, and what can be very different from our current theoretical expectations, etc. And these stellar mass observations of TianQin can also be linked with current ground-based detectors. So for example, I think we all know very well that LIGO and Virgo and Kagra has been making amazing detections on stellar mass black holes mergers, but their origin is still currently under debate. And the major reason is that many people, we still do not know, are they majorly coming from binary evolutions, or are they coming from the cluster dynamical process, or are they coming from the primordial black holes? There are many possible sources. And if they come from these clusters, either it's a globular cluster or the nucleus, the nucleus stellar cluster, in both cases, we expect them, it can happen through the binary to single encounter, and through the iterative process, it can grow closer and closer, then it will form a very compact binary until it merges. Now, this is very nice, but we cannot distinguish them from the binary evolution channels, at least with the current LIGO-Virgo-Kagra observation. And this is something can be changed when TianQin or LISA is operation. The major reason is that we do expect some difference between the dynamical channel and the binary channel, which is that for the dynamical channel, we assume, we expect the eccentricity, the orbital eccentricity of the binaries to be quite eccentric, quite non-circular. But with gravitational wave radiation, there is some effect. We call this gravitational circularization. And once it's evolved into the stage of like 10 hertz or 100 hertz to the very, very late stage, like only seconds before the merger, that's exactly what we are seeing for LIGO-Virgo-Kagra, then the remnant eccentricity is relatively low, and the duration of the signal is too short to tell the difference between non-zero eccentricity to a zero eccentricity. But with TianQin and LISA in the millihertz band, these sources are still relatively non-eccentric, and even though it can be circularized, the very long duration observation from TianQin and LISA will make it possible for us to tell that, oh, this is a value, the eccentricity is such a value that is non-zero, and we can see this is coming from a binary, this is not coming from a binary evolution, this is actually coming from a dynamical channel. So this is what we can expect TianQin observation can tell us. And also we can use the TianQin observations to tell something more interesting on the other part. So there are some recent studies showing that it is possible that the stellar mass black hole binaries are not in an isolated region. I'm not talking about in a cluster. I'm talking about these binaries can be formed around a very massive third body, and there's two binary orbiting around a third body. They can have some properties showing up in the through some relativistic effects, and including maybe some Kozar-Ledov oscillation, something like that. And the existence of the massive object could influence the gravitational wave phase evolution, and then we can tell the existence and even some properties of the third body. So this is some very interesting new way to observe a hidden massive black hole. And yeah, so this is some picture I get from something that is illustration on the channel I mentioned, the AGN disk channel. Some people argue that it is a very efficient formation channel for the binary black holes, that is the AGN disk. And if we assume this AGN disk orbiting around the AGN by an eccentric orbit instead of a circular one, then we might be able to pinpoint the properties of the disk. I'll get to this point later in more details. And the second part on the science we can obtain by TianQin is this formation and evolution of the massive black holes. So now the birth and evolution of massive black hole is still under debate. There are some existing theory on this stellar remnant. Basically, we call this POP3 or light seed channel. That the massive black holes we observe today originate from 100 or 1,000 solar mass black holes, originated from very early stage of the universe evolution, and then through accretion and merger, it grows into the very massive black holes we observe today. But the problem is now these models cannot explain many massive black holes we observe nowadays. That the current observations shows that many massive black holes exist in very high redshift. That is when the universe is very young. So in order to explain that these very young and very heavy black holes, some people propose as massive seed black holes, which is that for the formation of these black holes, it also happens very early in the universe. But once it's born, it is very heavy. It can be as heavy as 1 million solar mass. So that we can answer this issue. But the problem is that for the light seed model, it's more supported by the stellar evolution. But for the heavy seed model, it's supported by the black hole observation. But the problem here is that it is only theoretical. There's no direct evidence for their existence. I can show some more direct observations indicating that with current observation there are some sources that has been very high in redshift, but let's see, the horizontal axis shows redshift. It is very high redshift, but the mass is very high. So in order to have the light seed model originating from 100 solar mass to evolve to this stage, you have to require some super Eddington accretion, which is not very likely to happen. While if it's a heavy seed model, then the explanation goes very well. But the problem is that nobody sees how a heavy seed model actually work. And this diagram also shows a similar thing. So the problem is that we want to have some smoking gun for the heavy seed model. And it is a very good thing if someone can have the ability to tell the difference between the light seed model and the heavy seed model. And TianQin have exactly this ability. So I'm here showing the diagram, which is from Hampu and Kohi, that what they are showing here is that for the stellar mass, for the current EM observations, like HSC and ALMA and Sloan, we can cover this parameter space. This is showing the mass of the massive black hole. In the horizontal axis, it's 10 to the 8th to the 10 to the 10th, and then it's dedicated to relatively nearby sources, so the redshift is not very high. And if we have JWST, with the JWST, we are able to unlock some hidden parameter space. That is, we can go lower in mass and we can go further in redshift. But in order to answer the question of the seed black hole, the seeding of the black holes goes in this red square. Okay, so that is very high in redshift. It's like 20 in redshift and relatively light in the mass, 10 to the power of 2 to 10 to the power of 4. So this region, as long as we have the ability to observe something happens in this region, that is how we can answer the question of the seeding mechanism for massive black holes. And TianQin have exactly this ability, but if you look at this contour lines from blue to yellow, these lines indicating what if a massive black hole merger in this region, and then the color indicates the SNR, and the bluest region indicates SNR of 10. So even if a merger happens in redshift 20, and as long as it has a large enough mass, we will be able to observe it and then tell if it's exactly the distance as well as the mass, these parameters. So with the TianQin observations, we will be able to answer the question on the formation channels on the massive black hole. And that's one thing that some people might ask, there is Lisa, then why another detector? And sometimes 1 plus 1 can be much better than 2. And there goes a very good example. And here we show the parameter estimation uncertainty 1 sigma region. And the red circle goes for the TianQin. The green circle goes for the Lisa. So in both cases, the 1 sigma region is very large. And individually, we cannot resolve the location very well. These two parameters we by coincidence choose to be the sky location for the source. But if we have both detectors operation in the same time, the coherent observation instead of some coincidence observation, the coherent observation using the much of the information, we can increase the accuracy by orders of magnitude. And you can see the zoom in plot. The sky localization area is much, much smaller than individual detectors can achieve. So in this case, a network is much more preferred than just individually operating. Okay, so the third aspect of science we can uncover for TianQin is sources around massive black holes. And it can usually go to the M-rays or M-rays. So the M-ray, if you can recall, is the extreme mass ratio in spiral. And correspondingly, the M-ray is something we call these intermediate mass ratio in spiral. Then the M-rays can be classified as light M-ray or heavy M-ray. For the heavy M-ray, it's very similar to M-ray, the central object being the supermassive black hole in the center of the galaxies. But for M-rays, the lighter object is something of the stellar mass. It can be a stellar mass black hole. While for the heavy M-rays, the outer object can be an intermediate mass black hole. So it's a SMBH plus IMBH. Now, if we are talking about the light M-ray, then it can be happening in a globular cluster. In the center, it can be a IMBH, while the outer light object can be a stellar mass black hole. So depends on the mass ratio, we can call if it's an extreme mass ratio or the intermediate mass ratio. But looking at the exact component, the M-rays can be classified as light or heavy. The important thing is that since we have the TianQin detector have better sensitivity at higher frequency compared with Lisa, so the purple line here is Lisa and the red line is TianQin. The lower it goes, the better sensitivity, and TianQin have better sensitivity in the higher frequency. And so the stellar mass black holes that can be observed by ground-based detectors like LIGO and Virgo, it can be better observed by TianQin. This is something that TianQin has an advantage of. Also, if you are looking at the M-rays, TianQin and Lisa have different advantages. So if we are talking about light M-rays here, showing here, now I need to explain how do we look at the diagram. The diagram shows the uncertainties for different parameters in different directions. Okay, so the smaller it goes, the better sensitivity because the smaller uncertainties you can go. And for this diagram, the light M-rays, we can see that the outer ring or the radar plot, it goes very large area goes to Lisa. And this is because for the light M-rays, the sources, the majority of the energy comes in the high frequency end. And because TianQin has the better ability in the higher frequency, so these sources are the ability in constraining these sources mainly contributed by TianQin. And you can see the joint observation of TianQin plus Lisa. It's relatively same as TianQin ability. Well, for the heavy M-ray systems, because the sources are heavier, and in this case, Lisa will be dominating the ability. The inner circle comes from Lisa, the blue one, and the yellow one, the joint observations are mostly determined by the Lisa observation. But so this diagram basically try to illustrate that the two detectors have advantages simultaneously, and you cannot replace one with the other, right? And for these sources around the massive black holes, I think recently we've been discussing something relatively interesting. As I mentioned earlier, that we were talking about the sources. Let me jump back towards in this diagram, right? Many people currently believe that it can be a very promising channel for generating stellar mass black hole binaries, that is in the aging disk. So there are many stellar mass black holes in the aging disk, and some of them might just form a binary system. And this binary system goes along with the aging disk around this massive black hole. We are asking the question, what if this orbit is not circle, but eccentric? Then these binaries can encounter different radius from the central black hole. And in this case, it means that with a classical Asian disk density profile, that means we will be encounter very different environmental gas densities along different time. So we ask the question, will it be possible with TianQin observation to uncover the density profile? And this is an illustration diagram here. And if we zoom in on this diagram and show the residual from the observation as well as the theory, and you can see the shaded region indicates the uncertainty, and our theoretical prediction shows that with the TianQin observation, we will be able to pinpoint the Asian disk density profile very accurately. So this is something that TianQin can do. Now we can move on to the third part of today's talk, which is some progress on the data analysis. So the first case that I think in this section, I want to highlight two things that TianQin might have special advantage. The first thing is massive black hole binaries. For LISA, the more famous counterpart, we have a heliocentric object. Now this means the source is the constellation is very, very far away from the Earth, and the data transmission, we have to rely on some relatively big machinery on the ground to receive, and it is not guaranteed to have 24 hours observations. The current official schedule for LISA is that they have this 8-hour observation in real time, then switch to rest for 16 hours. The data will be accumulating on board. Then for the next 8-hour window, we transport the data. That's an official schedule by now. This is coming from the LISA Red Book. This means that we will be having some data window. We can do nothing but just wait for LISA. But for TianQin, because it's a geocentric orbit, the data can be transmitted to ground relatively easily, and we can almost be guaranteed to have a 24/7 real-time data transmission. What is the advantage of having this ability? You might ask this question. Now, there is a very interesting relationship between the ongoing observation time and the signal-to-noise ratio. We have this very nice analytical form on the SNR evolution. So the closer you go to the merger time, the higher SNR you expect to have. Okay, it goes very nicely through this line. And if you are talking about numbers, then in some cases, the final hour of the data might contain more than 99% of the SNR. So basically, if you miss the final hour, then even if you can predict some sky location, it will be very, very large. And it is basically impossible to pinpoint the actual host galaxy for the massive black holes in time. If you are going to talk about the multi-messenger observation, you have to have the ability to look at the object while the merger happens. And because the SNR accumulation is so sharp in time that if this merger happens in the window time period, then you have to miss the merger period. And this is something that TianQin can cover because we do not expect any delay, any major delay in the data transmission. So we use some method. I'm not going to the details, but we use some acceleration method we call this Hedge-Dine likelihood. It's not invented by us, but with this method, we can greatly accelerate this data analysis process. And with this as a core method to accelerate, we can achieve near real-time analysis that we basically refresh our understanding on the sky location as well as the source other parameters in every 40 minutes, sorry. So that per hour time, we can refresh the location as well as the other parameters. You can see as the time goes, larger and larger SNR we accumulate and smaller sky localization area it goes. So this is what we can expect to resolve. And the very important thing is to compare the sky localization area against a typical field of view of EM counterpart, EM telescopes. And here we show the field of view for three missions, including the CSST, the Vera Rubin Observatory, or LSST, and the Athena X-ray telescope. So you can see that for this source, which is relatively weak, in the final hour, it finally reached the very large area telescope, the LSST or Vera Rubin Observatory. So if you miss this 1 hour window, then you will definitely miss the area while the merger happens, and you cannot tell if there's any EM counterpart happening there. So this is the first case I want to highlight the special advantage of TianQin. The second case is related to the stochastic background. This is, as I mentioned, the incoherent stacking of different sources together. And one very interesting thing about the stochastic background is that with multiple detectors, we can actually do much better in some science objects. So for example, here we illustrate our idea of n-isotropic distribution. If you can recall, I'm pretty sure that every one of us knows the CMB, the cosmic microwave background. But we do also expect to have the cosmic gravitational wave background. Or maybe we can also say, looking at the origin, it can be astronomical gravitational wave background. So these backgrounds can be, n-isotropic. It's not necessarily being isotropic. So what's the ability for us to tell if it's isotropic or anisotropic? The key is to look at the spherical harmonic decomposition and to tell each different L values projections. And here, this value 0, 1, 2, and 3, and 4 is L number, right? This is a spherical harmonic indexes here. And for different lines corresponding to using TianQin or LISA or TianQin 1 plus LISA or TianQin plus LISA. Sorry, ignore this third line. It's some details I don't want to go into too much. The point here is that for LISA, for the individual detector, the ability to constrain the L equals 6 component is very bad. It's only 10 to the minus 9 ability. Well, for TianQin plus LISA, for the combination, we can go much better. It's actually 3 orders of magnitude better. So the reason is relatively complicated in terms of mathematics, but the key point here is that the idea of using a detector network to respond to a stochastic background is quite different from a single detector. The response being different, meaning we will be having vastly different ability in discovering the anisotropy of the background. So the other thing is that for the stochastic background analysis, with only one detector, you can only rely on the so-called null channel method. But the problem for this method is that it is highly model dependent. This model, I'm talking about the model of the noise. You have to assume certain form of the noise power spectral density. Otherwise, you can do nothing on a stochastic background. While for the multiple detectors, we will be able to cross-correlating multiple detectors, and so that will give you the ability to constrain the background in a way that is model independent. So with TianQin, we will be able to recover the anisotropy of the stochastic background. And here I want to show you that this is a result with only one detector. And the anisotropy we can constrain is relatively bad. The injection is only 1 point, but the recovery can only goes like this two very big blobs. But with TianQin plus Lisa, the recovery can be also the input is 1 point, but the recovery can be much smaller. And if the injection, the left column is injection, sorry, the left column is injection, the middle column is output, the estimation, and the third column, the right one is the residual. Okay, so you can see that with TianQin plus Lisa, we can go much better with a value of L to 16 with TianQin plus Lisa plus Taiji. So this is how we expect that with multiple detectors, the science can be done in a much better way, right? And the other thing, still related to stochastic background, is the non-Gaussianity. So I'm not sure if you are familiar with the idea of CMB. In CMB, the cosmic microwave background, many people are interested in the inflation, and if there's some nonlinear activity in the inflation, it can cause this non-Gaussianity in the cosmic microwave background. And by using this, what we call the 3-point correlation function, it is possible to constrain this non-Gaussianity. So the 2-point correlation function, usually this is a angular power spectrum, which I think most of us are familiar with. It shows something about the Gaussian components, and the lowest order non-Gaussian components shows up in the 3-point correlation, and the definition is here. All right. So if we can observe some non-zero 3-point correlation, then we can tell there is non-Gaussianity in the background, and we can tell something about the inflation. So by applying two typical or two examples, we can derive the equations. The equations, you do not need to know the details. The only important thing I want you to notice is that these values we derive in the low frequency limit. So that is when the frequency approach to 0, we calculate this thing called the overlap reduction function. It is something indicating the ability of a detector or a detector network's ability to respond to a signal. All right. So this value, we notice it's not 0 if theta is not 0. That means if you have a detector network, then this 3-point correlation, the overlap reduction function for the 3-point correlation is non-zero. While if you have only one detector, for the one detector case, you can just assume it to be like two detectors being at the same place at the same plane, right? So the theta goes to 0 and all the response goes to 0, and it drops to, in this diagram, it drops to 0. So this is something distinct, distinguishing the ability from a network and a detector, a single detector. That is, with a network detectors, we can measure the non-Gaussianity very well in the low frequency region. that is goes to this equation because when we have a network, the theta is not zero, and when we have only one detector, equivalently theta is zero, and we have no ability to constrain. And corresponding to some parameters, we can try to constrain the nonlinear parameter during the inflation. And currently, the observation from Planck can only give you the exclusion above this region. While with Tianqin and Lisa and Taiji, we can exclude some part of the parameter space, but with a detector network, including Tianqin or Taiji or Lisa plus Taiji, then we can exclude much larger parameter space, at least one order of magnitude better compared with one single detector. So to summarize, I hope that I've convinced you that Tianqin can, by using the Tianqin, we can help us to understand the physics related to the binary evolution and the formation and evolution of massive black holes, and also the immediate surroundings of the massive black holes. And especially, Tianqin have the ability to distinguish the formation channels for the binary black holes or binary white dwarfs, and it can also distinguish the seeding models for the massive black holes. And there is some total complementary between Lisa and Tianqin or Taiji and Tianqin. And there are some progress on data analysis, and especially there are some speciality from Tianqin that is we have the ability to perform a near real-time analysis, and also we can have a very good contribution for the stochastic background. With stochastic background, we can have much better resolution as well as non-Gaussianity. And that is the end of my talk. And if you are interested please talk with me through this email. And that's the end. Thanks a lot for your attention.
Thank you, Yi-Ming, for this really nice talk. Are there any questions? Please
I
simply unmute yourself or
have two questions.
Yes.
yeah.
Hello. Sorry, I missed
Hi.
the first 15 minutes of your talk, and because I had to talk to my students. But I'm
Mhm.
wondering, did you talk about constraining gravity, like tests of gravity?
Uh, I'm very sorry that I didn't cover that. That
Okay,
is because my
Mm.
topic is gravitational wave astronomy with Tianqin. So I
I see.
deliberately not mentioning any of that, but there are a lot of papers from our group working on
Right.
how Tianqin can be used to constrain alternativity
Mm.
theory of gravities, and definitely this
I
is a
see.
very good tool to do
I see.
that.
I
Yeah.
see. And so maybe then let me ask the cosmology question. So your last few slides is about cosmology, right? And
Uh, mhm.
I just want to make
Go
sure I'm
ahead, please.
following. Are you saying that you can I just want to understand the broad idea here. Do you
Mhm.
for example, what is this theta naught? I didn't quite catch. What is this parameter?
Oh, sorry. So this, well, I think you might be asking this one, right? The FNL.
So you're already talking about the 3-point function.
Yes, yes.
Okay. Yeah, because you first mentioned the 2-point function. So I'm wondering, can you detect the 2-point function?
Um, well, if we are talking about two-point function, then
Yeah.
the best way to illustrate is actually this, right?
Mm,
So, well, okay,
mm,
we can also show the L
mm,
being the spherical harmonic index here,
mm.
and we can only go to, compare with CMB
Right,
counterparts, it's very, very
right.
low.
That's what I'm
But
actually wondering about. So usually we talk
Mhm.
about the 2-point function in the sense of detecting CMB B modes, right? And I'm just trying to have a rough physics sense of how your observations complement the observations of CMB B modes.
Good question. So we are not talking about CMB. When we are talking about CMB, it's a
Mhm.
microwave background. It is
Sure,
using
sure.
the
Yeah, yeah,
microwave observations.
yeah.
Now we are talking about the cosmological or
Mhm,
astrophysical
mhm,
gravitational wave background.
mhm.
Okay, so this is the background that we expect to see in a gravitational wave channel, and we are asking if we have the ability to observe the gravitational wave sky, then how isotropic or anisotropic it is. And this is ability we can see. We cannot have very high angular resolution. That's a pity. But we do have some ability if it's a large variation in sky. And one step further goes to the non-Gaussianity, but that's a different story.
I guess maybe to make my question a bit more precise, are you able to distinguish between primordial gravitational waves and just stochastic sources from astrophysical backgrounds?
Excellent question. So, sorry, I didn't cover that in this slide, but yes, it is a very good question, and we have some publications covering that, and the answer is yes. But that goes to the spectral shape of the background. So we do expect certain patterns for astronomical sources. We have a certain expectation for the power law and another shape for the cosmological origin. And using this shape in the frequency domain, we can tell if it's stochastic, if it's cosmological or astrophysical.
So would you be sensitive to, I think what cosmologists call NT, the tilt of the tensor spectrum?
Uh, to be
Like,
honest, I am not
yeah,
very, yeah, I'm not an expert in that, so
okay.
I'm not sure
No,
if we
no
can do
worries.
it or
Yeah,
not.
no
Yeah,
worries.
I'm sorry.
Because you talk about the spectrum, so I thought that maybe one way to distinguish is that you can even measure NT, the slope of the power spectrum, and then maybe you can compare it to the other slopes from different sources and so on. I thought that's what you meant, but that's okay. I think, um, but are you also saying that you can even reach the sensitivity of um measuring the 3 point, I guess you're saying that you don't just mean primordial then, right? Yeah, I think that's your slide. I think that's what confused me. When you talk about
Mhm.
the 3 point function, you don't just mean the primordial 3 point gravitational wave function. This can be from anything. Is that right?
Um, so yeah, it's not exclusive in the
Mm,
sense that we do not require the source of this non-Gaussianity coming from
mm,
cosmological.
mm.
But if it's cosmological, then what it corresponds to
Mm.
is this diagram,
Yeah, this is the
basically.
thing that I was wondering about. Yeah, yeah.
Mhm,
So
mhm.
because in fact, my understanding is that the cosmologists also have not gotten any non-Gaussianity. Even I think the temperature. This is not related to gravitational waves itself, but just the temperature fluctuations. They haven't gotten even to the cubic uh, uh, FNL as well. But now you're talking
Mhm.
about the tensor FNL. Am I right? You're basically trying to detect the analog of the tensor FNL. So I'm wondering
Yes, I
whether,
think you might be right. Yes,
yeah,
yes.
I'm wondering how
Mhm.
competitive, in other words, is it possible that you might detect it before the cosmologists do it?
Uh, I mean, I agree that it's maybe not best motivated by theory,
Okay.
but again, we can add some extra, exclusion region in the Pratt space.
Mhm.
So that's my way to. Well, also, when we are talking about non-Gaussianity, again, it's not necessarily to be cosmological origin. It can be astronomical
I
origin.
see. So
Mhm.
do you have any, as since you emphasize you're talking about astronomy, are there specific sources that you care much more about regarding the 3 point function related?
Uh,
Yeah.
well, the non-Gaussianity, well, how should I say this?
Mm,
There are actually quite a lot of people in the field of stochastic background field
mm, mm,
talking about non-Gaussianity in a quite different way,
mm,
which is the time domain property. It's like popcorn-like feature, and we are using a very different, I think, first of its kind way to illustrate the non-Gaussianity and building a link to the CMB counterpart. But to be exact, the sources, well, all these sources, as long as it's not into a very large cosmological distance, right? It's relatively local. Then and also the source number is not many. Then it is certainly naturally not Gaussian, because the Gaussianity of the source in astronomical sources is only guaranteed by the big number law. And if you do not have big number of sources, then it's not Gaussian.
I see. I see. I guess my last question is that how do you complement the PTAs?
Sorry, maybe I hate to interrupt, but we have also other questions, so maybe we should also give somebody else a chance to ask a question first.
Thank you very much. Yeah.
Thanks, Yi-Jun.
Yeah, thank you. Can you hear me?
Yes, I can hear you, Rana.
Good. Yi-Ming, yeah, thank you for a very nice and interesting overview. Just good to remind us about TianQin. I have a question because we are interested in the AGN disks, and the objects, the binaries in this AGN disk. It was a bit fast. Can you explain again how you plan to infer the density distribution from TianQin observation? Is it by populations of binary black holes in different places of the disk, or is it by one binary migrating?
Yeah. So I think the idea is that if you imagine you have one pair of binary around the central AGN, if it's a circular orbit, then the radius does not evolve. But if it's a eccentric one, then the radius between the binary to the AGN varies. It goes wandering from further to closer, just like this.
Dimensions.
Yeah. So then
that's also electricity. If you have just from 250 to 450 Schwarzschild radii, or this is something. Well, maybe I have to ask later. So it's wandering. It's going. It's a very wide, very.
Yes.
Anyway, so thanks. I mean, there may be more binaries, and it's very interesting, I think, because we really try to model this and of how many binaries we have there, and also black hole binaries. Yeah.
Yeah.
Thanks.
Okay, Cheo?
Yeah, thank you. Just a very quick question. So you said that TianQin has a better sensitivity compared with LISA in higher density, higher frequency band. So just wondering, is that simply due to that TianQin has a shorter arm length, or is there any other reason?
That's a very good question. Actually, it's a quite often raised question. So in a sense, yes. I think now you can look at this diagram, right? This is a typical diagram showing the sensitivity, and there are three parameters constraining the behavior of the sensitivity curve. L meaning the arm length, SA is the acceleration noise, and SX meaning the positional noise. And by tweaking these combinations of the three values, you can have different shapes on the sensitivity curve. The one dominates this shape in low frequency is SA, okay? And the high or low, how high or how low it goes in the bucket region is SX, okay? And then in what frequency the tail raise up is determined by the arm length, okay?
I see.
So you can say it's a combination of all these parameters, but yes, in a sense, the most important thing that we gain, let me go to the other plot, something like here. Yeah, we have better sensitivity with LISA mainly because it goes up in a relatively lower frequency, while we can keep it flat and rise in a higher frequency. So shorter arm length, better sensitivity in high frequency. Yes.
Excellent. Thank you.
Thanks for asking.
Are there other questions? Yes, Don Cruz.
Just a quick one as well. I got disconnected for a bit, so I don't know if you talked about this, but you talked about using this detector to check Gaussianity and the um well, I guess isotropy of the stochastic gravitational wave background. But can you also use it for checking extra polarization states beyond GR perhaps?
Yes. Actually, if you are interested in the stochastic background, then we haven't been covering that yet. We are working on that with the ongoing project on the parity of the stochastic background. And I think there are already existing publications on individual sources like using the white dwarf binaries to test the different polarizations, the non-GR behavior on the different polarizations.
Okay, but is it in principle sensitive to that as well, this detector, or?
Uh, the bottom line, I think that wait, I can't remember the exact numbers, but it is at least comparable with LIGO-Virgo Kagura ability, if not better. I think that's my understanding. Sorry, it's not my. I'm not the leading author of that paper, so I'm having a very vague memory on the work. But we do have a good ability in constraining including the extra polarization or the parity of the gravitational wave signals.
Okay, okay. Thank you.
Yeah, thanks for asking.
Other questions? If not, maybe I can ask one. Do you also expect to detect gravitationally lensed gravitational wave events? And roughly how many on which sources?
Good question. That's embarrassing. I didn't include that. There was some recent paper we worked out with some colleagues, and in one of the recent papers we published, it's actually led by Chen Xian's student and Gao Zuchen, and he revisited the chance of far away event, say a massive black hole merger, and how likely is it to be lensed. And we basically use a more correct way to clarify if it's lensed or not. And the conclusion is actually the rate is higher than previously expected. I think it's about 10 times higher. So I think every 100 event, we expect around one event to be lensed for the massive black hole mergers. And the lucky number here is that in a relatively optimistic scenario, the uncertainty is very high, so we cannot say for sure. But in the optimistic scenario, TianQin will be able to detect about several hundred of massive black hole mergers every year. So that means that every year we will be able to see about one or two or three of the lensed events, and for the 5-year observation, we can see about like 10 of the lensed events.
Okay, thank you. Are there other questions? If not, I stop the recording here.